Okay, second segment of chapter 7. So we've been talking about the quantum mechanical atom. We've been working our way through history. We were in the early 1900s and we got to the discussion on the electronic structure of the atom. So some clues come from the study of light absorption, right? So what we can see now is that we have a ground state electron. We're going to add one quanta or an h nu of energy, and that's going to transform that electron up to an excited state. So the electron itself is going to absorb energy and then what we call promote or move to a higher energy state called an excited state. Now, the other studies that come in are going to be light emission. And in that case, we have that excited state electron, and it's going to fall back down to its ground state. Okay, so then when the electron loses the photon of light, it's going to come off sometimes as visible light or as energy. And we're going to see that. And a lot of times the term we use there is it drops back down to the ground state. All right, now the other thing we want to look at is the continuous spectrum. So a continuous unbroken spectrum of all the colors. So for instance, visible light through a prism, sunlight, an incandescent light bulb, a very hot metal rod, right? So even though that metal hot rod, it's the reds, it doesn't cover into the blues maybe, but it's going to be a continuous spectrum. So it's every wavelength if you think of it as being chopped up. Now the other thing we have are discontinuous or line spectrum. Now here, what we're going to see is that it's broken up. You won't have all the continuous wavelengths. You'll have a wavelength here, then a big empty space, and then a couple more wavelengths maybe. So if we consider the light given off when a spark passes through a gas under a vacuum. So we'll put gas inside our vacuum tube here, and we'll pass a charge across. That electrical discharge will then excite the gas molecules, and of course there's going to be a spectrum that's going to be emitted when it goes back down to the ground state. And what we're going to see here is it's going to have a few discrete lines, and these are actually going to be like fingerprints for an atom. So these are called atomic spectrum or emission spectrum. Okay, but they're going to be typically they're discontinuous. So maybe you get 4 or 5 reds and then maybe a yellow or a blue kind of mixed in there. Okay. Now again, each element is going to have its unique emission spectrum. So if you ever wondered how we know what atoms are going to be seen on the sun or what we believe is up there, it's based on these fingerprint wavelength patterns. So a line spectrum then would look something like this. We take that gas, we electrically shoot off a discharge there. It's going to emit a light. We'll then send that light through slits, hit a prism, and then when we hit the prism and separate that light, what we'll see for a discontinuous or a line spectrum is individual wavelengths showing up. Okay, and of course, if I combine these wavelengths, that's going to give me the color of the light that's being emitted. So these are not considered continuous. So if they were continuous, we would have everything from here all the way to here, and we'd have all of those wavelengths. That would be continuous. All right, so atomic spectra then, again, these are the atomic line spectra, and again, they can get rather complicated because you're going to get several different wavelengths. The line spectrum of hydrogen will be the simplest because it's a single electron. So once a second electron gets in there, we start getting energies involved with the 2 electrons as well, right? They're repelling each other. There's going to be an energy associated there. All right, so the first success in explaining quantized line spectra, and of course this was what was first studied exclusively. And so we're going to see J.J. Balmer. Now he might not be somebody you've heard of before. He comes in on the scene and he found an empirical equation that's going to fit lines in the visible region of the spectrum. So he was trying to associate the energies seen in the atom with the line spectrum that's given. And the person that follows up behind him is going to be J. Radberg. Again, these names are probably not nearly as popular as, the Einsteins and these guys don't, Balmer has a series named after him, but not his own constant. So a more general equation that is going to explain all the emission lines in the hydrogen atom spectrum. So, and again, some of these lines are going to go into light that we can't see. So like the infrared and the UV. Now Radberg does get his own equation. He says 1 over lambda is equal to his constant over 1n squared minus 1n squared. So number of atoms there, number of atoms, right? Number of moles. So RH is going to be the Radberg constant. Lambda, of course, is the wavelength of the light being emitted. N1 and N2 are going to be whole number integers from 1 to infinity, where 2 has to be bigger than 1. If N1 is equal to 1, then N2, of course, has to be equal to 3, 4, 5, 6, 7, whatever it may be. Now, these can be used to calculate all spectral lines of hydrogen, okay, only hydrogen. Okay, the values for N correspond to allowed energy levels for that atom. Okay. Now, consider the Balmer series where N1 is equal to 2, and we'll calculate the wavelength in nanometers for the transition from N2 equaling 6 down to N1 equaling 2. In other words, we're going to take 1 over lambda is going to be equal to the Radberg constant over 1 over 2 squared minus 1 over 6 squared. Okay. And so that means we're going to have 109,678 per centimeter times 1 over 4 minus 1/36. Okay, so that's going to give us 24,373.9 per centimeter. So lambda then would equal 1 over that, which has to equal 4.10292 times 10 to the negative 5th centimeters times 1 over 100 times 1 over 10 to the negative 9th. Centimeters will cancel out, meters will cancel out, and that's going to give us 410.292 nanometers, which would be the violet line in spectrum. Okay. All right, so a photon undergoes a transition from N higher down to N equals 2, and the emitted light has a wavelength of 650.5 nanometers. What is the value for N higher? Okay, so we're going to take lambda is going to be equal to 650.5 nanometers times 1 times 10 to the negative 7 over 1 nanometer, right? So that's going to get us into centimeters. So that's going to equal 650.5 times 10 to the negative 7 centimeters. Nanometers will cancel out. Now we're going to take 1 over that in centimeters, which is going to be equal to 109,678. We're going to multiply that by 1 over 2 squared minus 1 over n squared. Okay, so again, we're looking for N2 here. Centimeters will cancel out. And so we're going to take 1 over 7.135. That's going to equal 1/4 minus 1 over n squared. That means 1 over n squared is going to be equal to 1/4 minus 1 over 7.135, which means that's going to equal 0.1098. And so that means n squared would be equal to 1 over that, which would be 9, which means N2 then would be equal to 3. Okay, now remember it had to be a whole number, so once we got to 9.1, we just had to take the square root of that 9. Okay. What is the wavelength of light in nanometers that is emitted when an excited electron in the hydrogen atom falls from n equaling 5 to n equaling 3? Here are your answers. And of course, you can pause here, work that out using the equation from a couple slides ago. Hopefully you came up with A, and so it would be 1 over lambda is equal to the Radberg constant times 1 over 3 squared minus 1 over 5 squared. Means 1 over lambda has to be equal to 7,799.30 seconds per centimeter. Lambda then equals 1 over 7,799, which means it's 1 times 10 to the negative 7 nanometers to get to centimeters. I should say centimeters to get rid of centimeters, so we're in nanometers. Centimeters cancels out. And so we get 1.28216 times 10 to the 3rd nanometers. All right, so what's the significance of being able to use the Radberg equations and all that good stuff? Well, the atomic line spectra is going to tell us when excited atoms lose energy. Now, only a fixed amount of energy can be lost, and that means only certain photons are going to be emitted. So an electron is restricted to certain fixed energy levels in atoms. That means that the energy of the electron then has to be quantized. Okay, so now this is just a simple extension of Planck's theory. So rather than saying we have a photon and just talking about photons in general, what this is saying is if we promote and demote electrons, the energy going in and out, right, has to be related to the photon. And so we have a quantized value, that quanta, if you will, that packet. Now, any theory of atomic structure has to account for this atomic spectra, which means we have to have the quantization of all the energy levels in the atom. So what does that mean to you? Well, if we think about regular good old-fashioned classical mechanics, our bunny here sees a slope, right? And so it's just going to roll on down. So we have the potential energy of the rabbit. Okay. Sorry about that. I had to take a little pause. Anyway, so we were talking about the potential energy of your rabbit. And so, of course, when we're looking at classical mechanics here, we have this nice easy slope. Whereas now we're going to get into quantum mechanics. What we're going to see is that the energy has to be quantized. So it's going to be like stairway. So that's going to have to go down by steps. So since the energy is quantized, only certain discrete values are going to be allowed. Okay, so the presence of continuities makes atomic emission quantized. So in other words, it's got to go by a discrete value, one step, then the next step. Now, the other thing I'll point out is I say it's like a stair steps, but if you know anything about stairs, this distance right here always has to be the same in like our house, like in our stairs for our house. Here it does not, okay? It's got to be, remember, an n value of quanta. So the first step could be 1 quanta, for instance, and then the next step could be 5 quanta, and then maybe 1 quanta, and then maybe 3 quanta. It just depends on the energy levels of the electrons. And so we won't worry about that too much. That's just sort of an FYI kind of idea. Now, the Bohr model of the atom. So the first theoretical model of the atom to successfully account for the Radberg equation was going to be the Bohr model. And this is the one that we kind of work with. It's also referred to as the planetary model. So a lot of times when students get to this level of chem, they've had it in high school and you've heard of this before, seen this before. At the very minimum, even at some of the lower levels of chem, I've come to the conclusion that it must be the Simpsons that has led to this idea because in the opening credits, they showed the nuclear power plant that Homer Simpson works at, and that has that nuclear symbol that we're so familiar with, right? And there's that sort of pseudo-nuclear symbol that we see. Now, the quantization of the energy in hydrogen atom, Bohr was able to use his model to correctly explain why the equations work for the line spectra that's seen. So what he proposed was the electrons are going to move around the nucleus like planets move around the sun. And that's why we call it the planetary model as well. So they moved in fixed paths or orbits. Okay, and each orbit, of course, has a fixed energy. So the model for the energy for the Bohr model of hydrogen, the equation for energy of hydrogen in the H atom, he said that E has to be proportional to minus 1 over n squared. And B is going to be equal to 2 pi squared me to the 4th divided by h squared. So ultimately, B is related to the Radberg constant, where B is equal to the Radberg constant times hc. So, or we can rearrange the equation and say E then is equal to negative B over n squared, which is then equal to negative RHHC over n squared. Okay, so again, B would be the Radberg equation fixed into that. Now this will allow for values of n equal to 1, 2, 3, 4, all the way out to infinity. And so n is going to be equal to the quantum number. So we call that the principal quantum number. And we'll use that to identify which orbit we're looking at. Okay, so the next thing we look at then, to make sort of sense of it, put a picture with that math, is the energy level diagram for an H atom. So obviously here we have our nucleus, and then if we think of these orbits going around and there's going to be energy levels associated with them, for an atom to move up from n equals 1 to n equals 2, I'm going to have to absorb some energy, right? That's what we've been saying the whole time. Whereas if I go down, I'm going to be emitting that energy in light. So now what we're doing is putting values on n equals 1, right? So this equation back here, when n equals 1, right, we have constant times constant times constant over what would be 1 squared. So it's going to give us an energy value for this, which is going to be negative B. When n equals 2, it's going to give us 0.25 B negative, right? So forth and so on. Okay, now that's the absorption of a photon, which means if we absorb that photon, the electron is going to raise up to a higher energy level. Now the emission of a photon then means the electron is going to fall to the lower energy level. And again, remember, going back to the beginning of this, our energy levels are going to be quantized, which means every time an electron drops from one energy level to a lower energy level, it has to be some sort of frequency that the photon is emitted, right? So these have to be within that same quantum, okay, which is going to yield you a line spectra. So for the Bohr model then, when n equals 1, we have the first Bohr orbit. So this is the most stable energy state. It equals the ground state, which is the lowest energy state. Now remember, this only works with hydrogen, and hydrogen would only have one electron. Okay. The electron remains in its lowest energy state unless disturbed. So how do we change the energy of the atom? Well, we're going to add energy. So we're going to hit it with some light. When we hit it with light, that light has to equal, remember, h nu. So E equals h nu. That's going to be our photon, our quantum. The electron is then raised to a higher n orbit. So whether it be 2, 3, 4, all the way out to infinity. The higher n orbits will equal excited states. And of course, whenever we have an excited state, we say that's going to be less stable. So the electron then will quickly drop to a lower energy orbit and emit a photon of energy equal to delta E between the levels. So now we can say that delta E, that energy that's going to be emitted, is equal to EH minus EL, which is the higher and the lower orbitals. Now, why does Bohr's model fails? Well, the theory could not explain spectra of multi-electron atoms. The theory doesn't explain collapsing atom paradox. And if an electron doesn't move, the atom collapses. Positive nucleus should easily capture an electron. Okay, so that's the theory of the paradox, the theory of the collapsing atom paradox. So it's not explaining why the electrons will move. In fact, it has nothing to do with the electrons moving, but we know that if the electrons stop moving, then we have a positive charge, we have a negative charge, and they have to come together. That's what has to happen. Okay, so if the electron doesn't move, then the atom will collapse. Now, positive nucleus should easily capture that electron. Now, a vibrating charge should radiate and lose energy. Okay, so another problem with it is that a vibrating charge should radiate and eventually lose its energy. All right, so in Bohr's atomic theory, when an electron moves from one energy level to another energy level, more distant from the nucleus, will energy be emitted? Will energy be absorbed? There will be no change that occurs in the energy. Light will be emitted, or it's something else. None of these answers make sense. All right, hopefully, remember I want the electron to go from a low energy to a high energy. That means the atom has to absorb that energy. All right, while the Bohr model failed to predict the line spectra of other atoms, it is historically important because, well, it was Niels Bohr's only major contribution to science. It introduced the existence of neutrons. Didn't see anything in there about a neutron, did you? It provided a way to measure the mass of electrons. No, that was Millikan. Millikan did that. It introduced the idea of quantized energy for electrons in orbitals, or none of those. Right, it introduced the idea of quantized energy for electrons in orbitals. So overall, his theory may have failed, but the man was definitely onto something, right? All right, so light exhibits interference. So now let's go back and look at our light. If you're not aware, light can have constructive interference. In other words, if I take a couple of different waves and I line them up and they are the same, their amplitude will actually multiply. And so we'll have them be added together. So the waves that are in phase lead to a greater amplitude. And again, I know some of you are electrical engineers and you may have already studied more about this than what I know. They simply add together, right? We can also have destructive interference. So now they're off, it's called out of phase. And of course, that's going to lead to a lower amplitude or maybe even no signal at all. So they'll just simply cancel out. All right, so the next experiment we're going to look at is the diffraction of electrons. So this is going to be pretty neat. So light will exhibit interference, also has a particle-like nature. And so because it has a particle-like nature, we can look at electrons. We know they're known to be particles, but they're also going to demonstrate interference the way light does. All right, it's called the double slit theory here. All right, so standing versus traveling waves then. So first thing we got to figure out is, do the waves actually move? So like if you look at a wave in the ocean, we know the wave kind of like goes across, right, and crashes. Or does the water molecule that's in the wave actually just go up and then come down, right? So if it's a traveling wave, this is produced by like wind on the surfaces of lakes and oceans where the water is being pushed, okay? A standing wave, however, is like produced when a guitar string is plucked. So it just vibrates up and down. So the center of the string will vibrate, and of course the ends would remain fixed. Okay, so hopefully that makes sense. Now, standing wave on a wire. The integer number n of peaks and troughs is going to be required. Okay, that means the wavelength is going to be quantized. So L would be the length of the string. Now we can relate the length of the string back to the wavelength. So wavelength would be equal to 2L over n. Okay, hopefully that's making sense. So what we're saying is the wavelength itself would be equal 2 times the length of the string divided by n. Okay, the number of peaks and troughs that's required. Okay. Now, how do we describe an electron? Well, it has both wave-like and particle-like properties. So energy of a moving electron on a wire would be equal to E equals 1/2 mv squared. The wavelength is going to be related to that quantum number. So wavelength is equal to 2L over n. Okay. So if we treat it like a standing wave, then half the wavelength must occur an integer number of times along the wire's length. Now, de Broglie is going to come along and he's going to set up an equation for this. He's going to relate the mass and speed of the particle to its wavelength, because we know that lambda must be equal to h over mv, where v is going to be equal to h over lambda m, right? So m would be the mass of the particle, where v would be the velocity. So we're going to use 1/2 mv squared, and we're going to use what we know about lambda and energy. We're going to combine those and get lambda equals h over mv. So starting with the equation of the standing wave and the de Broglie equation. So we can start with these two. Lambda equals 2L over n, and we know that v is equal to h over lambda m. We combined with E equals mv squared, substituting for v and then lambda, and we're going to get some crazy crap. Okay, so E is equal to 1/2 m h squared over lambda squared m squared, which is equal to 1/2 h squared over m lambda squared. E will be equal to 1/2 times that monstrosity, which is equal to n squared h squared over 8ml squared. If we combine these, then we can say that the energy then is equal to n squared h squared over 8ml squared. You're going to have to look at that a few times, I bet. All right, so de Broglie then goes on to explain quantized energy. And he says electron energy is quantized. So, small writing here. It's going to depend on an integer of n. So again, we're still going to worry about this quantum n. So E equals n minus 1, n equals 2, n equals 3. So as we go up in energy, right, he starts giving values for it. Energy level spacing changes when positive charge in nucleus changes. So if I look at bigger atoms, then that's telling me that the energy level is going to change. So in other words, it's not simply going to be 2, then 4, then 6, then 8, so forth and so on. Again, these values are going to be different depending on the nuclear charge. The line spectra will be different for each element. And so this is why the equation worked fine for one electron. But the minute I put a second electron in, it's not just the electrons' interaction, but also the protons are going to affect how that's going to work out. The lowest energy allowed is going to be for n equals 1. Okay, so your energy can never be 0. That way the atom can never collapse. All right, so calculate the wavelength for an electron. What is the de Broglie wavelength associated with an electron of mass 9.11 times 10 to the negative 31 kilograms, traveling at a velocity of 1.0 times 10 to the 7th meters per second? So lambda then would be equal to h over, and then we're told that the velocity is 1.0 times 10 to the 7th times v, or excuse me, times the mass, 9.11. Okay, joules will cancel out. Seconds will cancel out. Other second will cancel out. Kilogram will cancel out. 1m will cancel out. So now we've got 7.3 times 10 to the negative 11 meters. Okay, so the wavelength associated with an electron traveling at that velocity is pretty small. All right, Calculate the Broglie wavelength of a baseball with a mass of 0.1 kilograms and traveling at a velocity of 35 meters per second. Again, we'll pause for a second so you can work this out. You might have to go back a couple slides. Hopefully you come up with C. Again, he said lambda was equal to H over mv. So we're going to say 6.626 divided by the 35 meters per second times 0.10 kilograms. Got to make some unit correction here. Get the joules to cancel out, kilograms to cancel out, meters will cancel out, seconds will cancel out twice, and that's how we got to 1.9 times 10 to the negative 34 meters. All right. Order the following objects from the shortest to longest de Broglie wavelength, assuming they are traveling at the same velocity. Okay, so boil this down. What's going to be dependent here? What's going to move? I shouldn't say move the slowest because they all have the same velocity. What's going to weigh the most, hence give the smallest wavelength? All right, so we want the shortest to longest wavelength. The chemistry textbook, the neutron, the cell phone, or a sulfur atom. Since cell phone isn't one of the first things, we know it's going to be the textbook. Then it's going to be phone, and then a neutron or a sulfur atom, right? The whole atom, right? So it's going to be B. All right, so a little long of a segment there. We'll hit the next segment up where we're going to see wave functions. So again, we're moving through history. Sometimes looking at I shouldn't say wave mechanics, looking at the development of quantum mechanics can be somewhat mind-bending, because remember, a lot of these things are happening at the same time and over a brief stint of about 15 to 20 years. So sometimes it's hard to keep things from being confused. So you might have to take your time and work through each person. That'd probably be the best way to do it, I guess. And just look at what each person is contributing and then try to figure out how they're being added on to each other. All right, so it's probably going to be a few more segments here and we'll get this chapter knocked out. So stay tuned.